Right. So welcome to our interaction session for COL 874 module. We're going to discuss modules 176 to 180, and this is about verification and how to kind of reason about a program using logic and things like that. Uh, so far, when we talk about compilers, it's mostly analysis that is kind of what is also called syntactic analysis, in the sense that, for example, if we do constant propagation, you're only looking at one property, let's say whether something is a constant or not. So one can think of that as a syntactic analysis. Or if you're doing liveness analysis, or anything like that. So you're basically doing or common sub-expression elimination, loop invariant code motion, partial redundancy elimination. All these are kind of looking at specific properties individually. But what if you could express like the entire meaning of the program somehow in a logical language? And if you could do that, then answering some of these questions just becomes uh, kind of can kind of fall out from there. So rather than having to develop separate analyses for each and every property, you have a like a meta level analysis that just kind of tries to express the meaning of the program, and then you have some algorithms that extract the properties that you're interested in from the meaning that you have been able to figure out. Of course, we're going to find that there are limitations to how much meaning you can express and what are the limitations and so on, as we go along. But that's that, and roughly that's what that's why we are looking at all these techniques, and these techniques also fall in the purview of program verification, because when you try to express the meaning, you're basically trying to say you can really try talking about the semantics of the program as much as possible, and much deeper way than the syntactic analysis that I have learned so far in our compilers literature. Okay, over to you, Sayam.
Let's get started. Am I audible?
Yes.
Let's get started. First, let's recap what we saw last time. So we defined some process level metrics to determine how good the program is and how correct it is. But we also saw that it is not always sufficient to have this level of quality for critical applications that might include medical infrastructure, medical equipment, or space programs or stuff like that. We specifically also talked about the Ariane 5 launcher and how an overflow problem in that costs a lot of money, like 500 million and 2 billion indirectly. Uh, there was also an incident, a medical incident in which a radiation machine was outputting more radiation than was required due to a race condition, and that cost a lot of life. So uh, we saw that it is not enough to have bugs. It is not enough to have that kind of software quality for critical applications, as it is very critical. But most programs don't come with any kind of quality because it is very hard to say that the program is correct and will always perform correctly. Uh, so, what we are trying to do is a kind of a moonshot goal to guarantee safety and security in all the software that we make. We can do some of the stuff step by step, such as what we will do in this course, which is the checking the absence of large categories of bugs. Then we can move to improving the precision and scale of those improvements. And finally, we can move towards automation, where we would try to automate all the verification stuff. And so there was a code by Tony Hua, the construction application of a verifying compiler that guarantees the correctness of program before running it. And it is a very hard goal, though we are ambiguous about the term correctness here, and it could mean anything, but it is still a hard goal. So let's move on to our current module, which is assertion. So basically, what is an assertion? Assertion is a statement or logical predicate about the values that a program can, the values that a program variables can take at any execution point. And there are two main conditions that we could talk about. Precondition, which is the condition that is satisfied that we assert before the program has started, and postcondition is the assertion that we assert after the program has ended. They may or may not be true since they are only assertions. So, for example, for the program y equal x into 2, we may have a precondition that x is greater than 0, and post condition could be x greater than 0, and y is y modulus 2 is 0, or y is even, and y is equal to 2 into x. We could also have a post condition that y is greater than 0 and y is even. And so the assertion may be stronger in the first case and weaker, but both hold true in this case. And then we talk about the concept of partial correctness. So partial correctness is basically that if precondition P holds on entry of program C, and if the program execution terminates, then the post condition Q holds. And one important thing is that we say this is true if and only when the execution of C completes. So if, for example, if the program C never terminates, this condition is vacuously true. And so we can represent this partial correctness condition in the form of Hoa triple notation, which states that precondition and when the program C executes, then Q holds. So let's look at some of the examples for article notation. So we may have some tautologies like if P holds and C completes execution, then true holds, which will hold true if C completes. We may also have that if false holds and C completes, then Q holds at the end of it, because since false doesn't hold at the start of the program, then uh, it doesn't matter. It is actually true. We may also have that for non-terminating program, um, if P holds, then if C completes execution, then false holds. This can be true because C never holds. So it doesn't matter what's on the other side, what's the post condition. So we could replace it with any other condition. We could also have, say, C was y is equal to 2 into x. So if we started with the precondition true, then when the program completes execution, then y modulus 2 must be 0. Um, if x was 0, then when the program completes, then y is equal to 0. If x was less than 10, then when the program completes execution, y would be less than 20, provided there are no overflow and we are dealing with integers here. And similarly, if x was less than 10 and C completes execution, then y would be even. So we could have a lot of such combinations. Uh, we also talked about some more examples. For example, we may have this program sum is 0 and we sum I is equal to 0 to n minus 1 in sum. And so we assert that given the precondition true, when C completes execution, sum would be n into n minus 1 by 2. And these kind of assertions are more complex to make compared to what we saw earlier and may require deeper analysis of the program. Uh, so now we move on to abstraction. We saw in the in the previous modules what an abstraction is and how it can help us to determine the correctness of a program. So an abstraction is basically an assertion that holds. Uh, and so, for example, we may have this uh, y, the values of y at some point, y is equal to 2 or 6 or 8 or 10 and on and like that. And so we may assert that y is greater than 0 and y is even. And note that the assertion that we are claiming uh, could include more behaviors than what were actually shown by the program at that point. So We may even have trivial assertions at a point, and they will still hold. They may not be as useful of an abstraction as the stricter one, but they will still hold. And so it is important that abstraction can add more behaviors, but it cannot remove any. We then move on to the next module, invariants. Basically, what are invariants? So invariants at a program point is an assertion that holds or an abstraction during execution whenever control reaches that. So we may have we'll go with this standing example. This is the Euclidean division example in which we have x greater than equal to 0 and y greater than 0. Here x is our dividend and y is the divisor. And we set q to 0, r to x. And while r is greater than equal to y, we do this. At the end, we would get something like x equals qy plus r. Uh, let's analyze it further. We may have a precondition that x greater than equal to 0, 5 greater than 0, and this is our post condition that r is greater than equal to 0 and less than y, and q is greater than equal to 0. We may also add assertions at each program point. For example, after we have set q to 0, we will have x greater than equal to 0, y greater than 0, and q equal 0. Similarly, when we set r to x, we will add r equal x condition to that. When we enter the loop, we may reach the start of the loop either after several loops or when we enter it for the first time. So clearly, r will be greater than equal to y because the condition of while amounts to true. R is greater than equal to 0, it can be either seen from R is greater than equal to y and y greater than 0, or we can also see that if in the previous loop R was greater than equal to y and we only decrease it by y, then R is clearly greater than equal to 0. And we have q greater than equal to 0 because at the first entry of the loop it is clearly true, and in each iteration we only increase it by 1. This assertion also holds, uh, but some assertions may be more useful than others. For example, uh, um, I think I missed point. Here we were proving it by uh, doing induction on the number of program steps. So this is also called inductive invariant. So first we proved it for the base case, and then assuming it held at kth iteration, we proved it for the k plus 1th iteration. But the uh, assertion that we want to prove at the end, like x equal qy plus r, it may not be easily derivable. It may not be derivable from the assertion that we currently have. So we may want to add more conditions that will allow us to prove x equal qy plus r at the end. Currently, we can only say it for the case when the while loop doesn't run even once, because in that case it is clear that r equal x is less than y, and thus and q is 0, so x is clearly equal to qy plus r. But let's see how we can do it for the case when we enter the while loop. So we may add more conditions here. We may add the condition that x equal qy plus r at the start of the while loop and at the post condition as well. Um, so um, uh, if we do that, we can see how it holds. So it clearly holds at the when we enter the while loop for the first time, and after each loop, we may see how it holds. We'll see that in the next module. So the next module is about verification conditions. So let's see how we may do that. First, what is a verification condition? So verification condition is a proof obligation that is generated as part of a larger proof. we'll see what are the verification conditions and how they can be encoded as for triples or logical statements. So for the program that we had, we could divide it into three parts. First part is before the entry into the loop. Second part is an iteration of the while loop, and when the condition holds at the end of the while loop. And the third is when the condition doesn't hold at the end of the while loop. So let's see. For the first one, we have the precondition that x is greater than equal to 0 and y is greater than 0, and we execute the program p equals 0 and r equals x, and if r is greater than equal to y. So the condition of the while loop holds. So at the end of that, we have the post condition x equals qy plus r, and r is greater than equal to y, and both clearly hold. Um, we have the second verification condition for the execution of while loop at the end of which the condition still holds. So we will have x equal to y plus r, and r is greater than equal to y at the start, and we change the notation a bit and say that the new variable r or r dash is equal to r minus y and q dash equal q plus 1. And if r dash is greater than equal to y, so we'll have x equal q prime y plus r prime and r prime greater than equal to y, and both clearly hold from how we set r prime and q prime. And when we execute the last iteration of the while loop, we will have r prime equal r minus y and q prime equal q plus 1. And the while condition doesn't hold. So we will have that r prime is greater than equal to y doesn't hold, and so r prime is less than y also holds, and this also holds x equal to prime y plus r prime. So we have these three verification conditions that we formed by dividing our code into smaller code snippets. And so now that we have this whole program, the precondition is as given and the post condition, and we have the whole program. And so now that we have all the three conditions hold, the VC1, VC2, and VC3, we can prove that the verification condition invariant for the whole program holds, that the precondition and the whole program executes leads to the post condition. um, uh, we should note that this is a partial correction condition, and it only holds when completes execution. We are not talking about whether or not C will complete execution here. We just assume that it will, and give the proof accordingly. Let's talk about assignment verification condition next. So let's suppose we have the precondition, some precondition P of the program variables, and we do an assignment to X, some function of the program variables, and we have a post condition Q on the program variables. Uh, when we talk about this, we have to we can't exactly talk about this in terms of the C program statement X assigned E of this, because then we have to deal with the language semantics of the different languages. So we like to talk about it in higher logic, and so we can encode it as a condition. Uh, as a logical condition. And so one way was given by Floyd. In this, we say that for all the program variables, there exists x prime such that uh, p of x, x replaced by x prime and other program variable holds, and we set x equal to e of x prime and other program variable. If this two conditions hold, then it is true that q of x and other program variable hold. And we can see that it is equivalent to what we expressed here in the for triple notation. We can also use the for representation for the same. In this, rather than making a new variable and replacing it, we say that for all xy, if the precondition holds on the program variables, then the post condition holds on the program variables, where we replace the variable x that we had assigned to with the new value that it has. So this is the for notation. So and here we say that b is b evaluated with x replaced by a. It represents the substitution of a for x and b. So the thing that we used here. So let's go with an example. Here, suppose we have the statement x is equal to x plus 1, and we have the precondition that x is greater than equal to 0, and post condition that x is greater than 0. So for in the Floyd notation, we can say for all x, there exists x prime such that x prime is greater than equal to 0, and x equal x prime plus 1. That implies that x is greater than 0, and we can prove it using our logic statements. Similarly, we have for all x, x is greater than equal to 0, implies x plus 1 is greater than 0. Here we have basically what we have done is we have the post condition x is greater than 0, and here we have replaced x with x plus 1. So when we do that, we basically get this x plus 1 greater than 0. So yeah. So let's move on to the next module. In this, we will see how to provide verification condition for conditionals or if-then-else statements. So suppose we have this program. We have the precondition P and post-condition Q, and we have the program. If B of program variable holds, then we execute something, else we execute something else. And here we can suppose that we get some conditions from some oracle, say at the program points at the start of the if loop, at the end of the if loop, at the start of if statement, at the end of the if clause, at the start of else clause, at the end of else clause, P1, P2, P3, P4. And we don't know how we got this yet, but let's go with suppose we have these, then we can state some verification condition for these. Suppose we have the verification condition 1, that if P holds and B holds, then P1 holds. This is a verification condition for P1. Similarly, we can have a verification condition for the program between P1 and P2, but we won't talk about it here, as it could be it could lead to separate analysis, and we can do it for can do it using induction later on. Then we will have for the P3 condition, we can have the verification condition 3, that if P holds and I think there is a misprint here, so it should be not of B. So we enter the else clause if B doesn't hold. So if we have that P holds and B doesn't hold, then P3 holds. And so this is a verification condition 3, and the we will similarly have verification condition 4 that relates P3 and P4 and the program in between. And finally, we'll have a verification condition that relates P2 and P4 with Q, that basically states that if P2 holds or P4 holds, then Q must hold, since we can exit the if-else clause from either the if side or the else side. So we'll have if either P2 or P4, then Q holds. So let's see it with an example. Suppose we have the program if x greater than equal to 0, then we just skip or the no op, else we assign minus x to x. So suppose that we have also have the precondition x is equal to x naught, and our post condition is x is equal to mod of x naught. So suppose that we are given P1, P2, P3, P4 as given here. So suppose P1 is x equal to x naught and x greater than equal to 0. P2 is x equal to x naught and x greater than equal to 0. P3 is x equal to x naught and x less than 0. And P4 is x equal minus x naught and x is greater than 0. So let's see the verification condition for these. For the first condition, we will have x equal x naught, which is the precondition, and x greater than equal to 0, which is the uh, condition for if. If these two hold, then x equal x naught and x greater than equal to 0 holds, and this holds trivially. Uh, then we'll have the second condition, second verification condition, and this also holds since the middle part was a no op, and so it is similar to the first one. Um, uh, uh, for the verification condition 3, we have x equal x naught and not of x greater than equal to 0. This evaluates to x equal x naught and x less than 0. And this holds because not of x greater than equal to 0 would be x less than 0. Uh, for verification condition 4, we use our substitution. So we have x equal x naught and x less than 0 at the start of the loop, start of the as the precondition. And when we do x replaced by minus x, then we have minus x equal to minus x naught and minus x greater than 0, which is basically post condition in which we replace x with minus x. And this also holds because x was equal to x naught, so minus x is equal to minus x naught. And since x was less than 0, we can take x to this side and we get minus x is greater than 0. And so the first four verification conditions hold. And then we can talk about the fifth verification condition, that if x is equal to x naught and x is greater than equal to 0, which is the P2, and or x equal minus x naught and x greater than 0, which is P4, then x equal mod x naught. We can see it for P2 that if x equal x naught and x is greater than equal to 0, then x is clearly the mod of x naught because x naught is greater than equal to 0. And if we have x is equal to minus x naught and x is greater than 0, then x naught must be less than 0. And so x equal minus x naught evaluates to x equal mod x naught. And so the fifth verification condition also holds. Note that the verification conditions are a bit general, that we just had to find the four conditions P1, P2, P3, and P4, and if all the five verification holds for any of those P1, P2, P3, P4, then our precondition and post condition hold for this whole program C. Uh, so with that, we move on to the next module, which was about the sequence operator. And in this, we have basically sequence operators, two statements separated by a semicolon. So we will have something similar to that here. And so then we talk about the verification the assertions similar to before. So suppose we have the precondition P and post condition Q, uh, and then we can have a condition in between, say P1. Uh, we have to find that, we haven't found that yet. But suppose we have some condition in between, then we can have the verification conditions uh, that can be represented in for notation as for all xy, if p holds, then p1 holds with x replaced by f, which corresponds to the first statement. And similarly, we will have a second condition for all xy, if p1 holds, then q holds with y replaced by g. And so we may want to choose so basically this can be represented as this, where p s1 p1, where s1 is the first statement, x assigned f of the program variables, and p1 s2 q, where S2 is y assigned g of the program variable. And so we may want to talk about what could be P1 here. So we can take a guess here, and not a guess, but we can assign it something. So for example, we can assign it q with y replaced by g, and this clearly holds. The second verification condition clearly holds, because if we replace p1 with q replaced uh, uh, q with y replaced by g, then the two are basically equal, and so this clearly holds. And this pre-image of q at the previous program point is called the weakest precondition, and we'll see this in later module. So suppose we choose that. Then we have the P1 replaced by Q and Y replaced by G. And then our first verification condition becomes for all xy if P holds. Then Q holds with Y replaced by G and X replaced by F. And here the order of replacement is important, that we first replace Y with G, and then later on replace X with F. If we change the order, then our result might change. And so we do that. And so our final condition for our sequence of operations becomes for all xy if p holds and q holds with y replaced by g, x replaced by f. And we may do this for multiple statements, just not two. We may do it for multiple with for bigger sequence of operations. Just that we'll have more replacements to do, and we do that in the reverse order. Uh, but as we can see, it allows us to remove a condition P1, but instead we will have to do more replacements here. So that is one thing of something. And this was it. And no, the module. Thank you.
Okay, thank you, Sayam, for the nice summary. So yeah, let's open the floor for questions. Let me start off with a question. So, at the beginning of this module, we discussed why we are even discussing about verification and how it contrasts with all the other kind of compiler analyses that we have learned so far. And I use the phrase that maybe we're going looking at specific properties, and and that's why you can call it a syntactic analysis. Whereas here we are looking at trying to encapsulate the meaning of the program. And in general, encapsulating the meaning of the program is a super hard problem, but you try your best effort. And how are we encoding the meaning of the program? We are encoding the meaning of the program using this logical language, which we are assuming here to be the first order logic language. So first order logic, you are allowed to quantify over values. That's what first order logic means. And some of the formulas that you saw had the for all operator and there exists operator and so on. And those are kind of, features of first order logic. And using those operators, we are basically representing properties of either the whole program. For example, we represent the property of a whole program by saying, by specifying the precondition and a post condition, saying if this is the precondition, that would be the post condition, and we try to make it as general and as precise as possible. The other way we can do it is we can say invariants, and we say, okay, at this point, this property definitely holds, and that property you encode using first order logic, right? So, I mean, in many ways, what we are doing in verification is not very different from all the compiler analysis that we have studied so far. I guess the major difference here is in compiler analysis, looking at specific properties. Here we are trying to kind of identify like wider properties or so-called meaning using a much richer language, such as first order logic. And you can of course make the language even richer. First order logic is just one of the choices that you could use to represent the meaning of a program, by the way. All right. So taking off from that, how does, I mean, and the other things we kind of learned was how to kind of actually be able to check certain whole triples or certain partial correctness properties. And we said, okay, the major idea that we got introduced to was induction, and say, okay, if there's a loop, then you need to use induction. I think that was the major idea. Other things were kind of saying, okay, if this holds, then that holds, and we're assuming that there is some kind of first order logic. I mean, that's the logic that we're using. There's some kind of solver for the first order logic, so we can give it some kind of formula in first order logic, and that solver will say yes or no, depending on whether that formula always holds or does not always hold. So and so we said, okay, these are these verification conditions, and we also gave an algorithm on how to check the verification conditions, and so on. So and generate. So given a program, how to generate the verification conditions. For example, for VC, we still not discussed how to identify the intermediate assertions, those candidate assertions P1, P2, P3, P4, etc. We said, if there exist any such intermediate assertions, then we are okay. But even let's say that those are kind of there, we kind of gave an algorithm, assuming those, then Oracle has already given us, applied us all the intermediate assertions. We still have an algorithm to basically check whether the end-to-end partial correctness condition holds or not. And we kind of gave an algorithm and say, okay, you kind of look at every consecutive pair of assertions and the program between them, and you basically prove that, and you are okay. And for a loop, you basically also look at the back edge and things like that, and that's what the algorithm was. Now, can you relate this algorithm to, let's say, any of the algorithms that we have learned earlier in the compiler course? In particular, let me give you a hint. I mean, like the data flow analysis algorithm. I mean, is there something common, and what can be represented in what terms and how and so on? What are the connections? So let me put it another way. Let's say, this verification condition checking algorithm that we have discussed, can it be represented as a data flow analysis?
I mean, now you would have values as predicates, and you would also take the path conditions into account, which we did not do before in the DFA. Usually.
No, I mean, that's a little bit vague answer. So when I say can something be expressed as a DFA, I would like the answer to the following. What's the transfer function? What's the set of values? What's the semi-lattice? What's the transfer function? What's the meet operator? Right. I mean, maybe like the semi-lattice is specified by the meet operator. So what's the set of values? What's the meet operator? What's the transfer function? Those are the three what's the direction, right? I mean, those are the major properties of a DFA, right?
So maybe we could define it in such a way as the direction is from the start block to the end block. The meet operator could be intersection of different predicates. So if let's say when
you say start block to the end block, you're basically saying it's forward direction.
Forward, yeah, forward, yeah. So the meet operator could be intersection. So if I have predicate P1 coming from one branch and predicate P2 coming from other branch, then the resulting predicate is intersection. So both of them must hold true if I'm reaching that condition. Both, or wait, is it intersection or union? No, it must be intersection, right? Because only if one of them holds true, that does not work. Both of them must be true. And then the transfer function could be these replacement operators which we talked about, right? So you take the initial predicate, you replace all the variables by the so whatever assignments you have, and that gives you the predicate at the out of the basic block, something like that.
Okay, all right. I'd like to emphasize here, right? I mean, like we're assuming that the predicates have been given to us by the Oracle. I'm just asking about the checking algorithm, what the checking algorithm represented as a DFA, not really the algorithm to identify what predicates there are, because we haven't really talked about any algorithm that can identify what the P1, P2, P3, P4 will be. We're just assuming that P1, P2, P3, P4 are already available. I'm only asking what is the algorithm for checking. We already discussed that actually, but how can I represent it as a DFA?
We could represent it as a backward DFA, as we saw in one of the examples when you had the sequence operator, that we had the post condition, and we kind of briefly discuss about having the weakest precondition, having it propagated backwards. So let's say if we have all these predicates that you're saying that are given to us, we start from the end and try to go backwards to verify if the if the precondition is sufficient to uh, I mean assert that the post condition is true.
Okay. Once again, I think you're making the mistake of trying to. I mean, although in the last module we basically discussed how to identify the P1 or what could be a candidate for P1 for the sequence operator. I guess I'm not really asking about that. I'm asking about let's say the predicates are already available to us. We know. I mean, they're property of the program already. Right? Those P1, P2, P3 have been annotated by the programmer for us. All we are doing is checking, right? I mean, that's all. So, what's the algorithm for checking?
We can have a forward DFA with like, values would be the set of all predicates. Like the set of values is the set of all predicates on the program variable. And the transfer function is basically what we have discussed, like, so for assignment this is this, for conditional this is this, and if the final value that we get, if that implies the predicate over that program point, then it's fine. If it doesn't, then a DFA basically fails to prove that.
Right, right. Yeah, I mean I think that's the kind of answer that I had in my mind as well. Basically, the idea is that maybe the values are true or false, which basically say whether the predicate that's been given to us, does it actually hold or not? Because it's the only thing we're doing here is check. So, the value that the set of values is just true or false. The meet operator is logical and, right? I mean, that it should be true for on all incoming paths. And the direction is forward. And the transfer function is basically that, if I, across an assignment statement, it's substitution. Across an if clause, it's a not B. It's an sorry, and B will basically say that the condition actually holds. I mean, exactly what we discussed for if then else kind of thing. I mean, we basically look at each construct separately. Like, this is what you do for assignment. This is what you do for if then else, and so on, and this is what you do for sequence, and so on. So I mean, the values are just true and false. The meet operator is logical and the transfer function is what we discussed. So I guess that's what it is. And so that basically means that so I mean, actually, if I just change my all these P's from first order logic to, let's say, a much more restricted set. So I just changed my the language from which I'm drawing these assertions. Rather than using first order logic as a language from which I'm drawing these assertions, let me make it like just for the constant propagation, whether something is a constant, whether something is not a constant, or whether something is unreachable, the three values. It's basically the same kind of thing, except that here it's exactly the same thing, and we basically specify it. So really, from a framework point of view, we haven't really made any difference. The major difference we've made is change the values from specific values to like first order logic values and check whether they hold or not. And that also means that, so what's the advantage of doing this richer language and richer syntax like first order logic? The idea is that you can you can have a single analysis that tries to infer rich properties of the program, rich assertions, and then from those rich assertions, all the other specific properties will just fall out. So example, constant, whether something is a constant or not, is expressible in first order logic. Just as say for all x is equal to c, and that basically means it's a constant. It's going to be a constant, and if you don't have it, then it's not a constant. Or if the predicate is false at a particular point, that basically means this whole place is unreachable. So that's basically the unreachable value in our constant propagation DFA, right? So I guess I'm saying that this whole verification business is kind of a richer language overlaid over our DFA framework. That's what it is. So far, we have talked about how to do verification, how to do checking of a given set of assertions, and assertions are already available to us. Next week, we're going to talk about how to identify what these assertions are automatically. right? And it's going to turn out that because the language has become richer, it's not necessarily possible to identify the most precise assertions at every point, or sufficiently precise assertions so you can prove end-to-end properties. I mean, that problem is actually an undecidable problem, as we're going to look at next time. And why is this difference between, so when we talk about constant propagation or any other kind of analysis that we've seen before, DFA analysis, we never talked about undecidability and so on. But now when I talk about this first order logic, this identification of these intermediate assertions seems like a pretty hard problem. I mean, in general, when I have loops and stuff, we looked at the example of the Euclid GCD algorithm and things like that. So that seems much harder than to do automatically, right? What is the reason? I mean, both are DFAs, just a difference of values. Why do you think this problem is harder and that problem was easier?
Yes, so in the case of a first order logic, the height of the similarities is going to be infinite because we can't really weaken. Because, for example, if you have a predicate of a first order logic and it is containing for all condition, then that for all can be over a infinite number of states, right? And then we can't really find the next weaker condition because there are infinitely many next weaker condition where any, okay, so if X is n states, then the next weaker condition is any n-1 states solved. But since n is infinite, we can't really exactly find it. So the height is infinite in this case.
Okay, thank you, Indrajit. Yeah, that's exactly the answer I was looking for. The height of the semilattice of the values of first order logic predicates, we haven't been able to bound it, or we haven't yet decided that we're going to bound it in some way or something like that. If we allow free form predicates in our first order logic values, that basically means that the semilattice that is, and the meet operator is going to be, intersection or logical and or whatever, depending on how you're looking at it, then it's not going to yield a finite height semilattice, because it can just keep getting deeper and deeper and deeper as we go along. So I guess those are the primary differences, and verification is basically richer syntax, richer set of properties, but that richness comes with a cost, which is the infinite height of the semi-lattice, and so you need other ways to bound the height of the semi-lattice. Because if the semi-lattice is infinite, you don't have a general algorithm, because your algorithm may run forever for certain programs. So you need other ways to kind of be able to make things tractable or write complete algorithms, that total functions or something like that, yeah, terminating programs. Okay. The other thing I want to really emphasize is that this is a partial, all the discussion that we've done so far is about partial correctness. So the verification conditions that we have discussed, they do not really talk about, oh, the program will definitely terminate or anything like that. They're just saying, if the program takes this path, then we are done, we are okay. If it takes this path, we are okay. But does it ever take this path? We don't really say, right? Does it ever exit the loop? We don't really say. We say, if it exits the loop, then this will hold. But we never say whether, oh, it'll definitely exit the loop at least once or something like that. We don't say that. And that's, we're approaching this step by step. The kind of techniques that you need to prove partial correctness are different from the kind of techniques that you need to prove total correctness. Total correctness includes termination. So total correctness, as we're going to see later on, is basically that program terminates and you're sure that this will happen eventually, and then it holds. The post condition holds, and so on. So yeah, that's another thing. Right. Okay, so looks like are there any other thoughts, questions, comments, or? Okay, in that case, let me just stop recording.